Hello, everyone, and welcome back to the 2020 Bibliometrics and Research Assessment Symposium. My name is Chris Belter, and I am one of the co-hosts for this particular event. Before we get started for our next session, I have a couple of quick announcements, just in case the folks have joined who weren't on any of the previous sessions. So as I mentioned, we are recording this particular session, but we're not recording the attendees or the chat, so feel free to continue to participate and know that you're not going to be a part of any recording that we make. Audio for attendees is in broadcast only, so you don't need to join the audio session to get audio. Attendees are muted and are unable to unmute. So if you have any questions, please use the chat box to get in touch with me, or get in touch with us, excuse me. You can use the chat box to ask questions for our speakers and to troubleshoot any technical issues you might be having. We do have some folks monitoring the chat for questions and for technical issues, so please send all chat messages to everyone. Not all attendees, not all panelists, please send it to everyone so that way we can actually see those questions and those comments, and we'll be able to address them. Finally, web captions are available in the multimedia viewer panel in the lower right of the WebEx events box, and they're also available in the URL that was shared in the chat and on the Slack space. So with that, we are going to go ahead and jump into our next set of presentations. We're going to start out with a series of presentations on analytical methods and approaches for understanding particular publication sets and publication portfolios. Up first, we have Jennifer Jacoby from the U.S. Department of Energy to talk about methods and metrics development for some of their journal articles. So Jennifer, are you there?
I'm here. Thank you, Chris, and thank you to everyone at NIH for putting this symposium together. We've learned so much so far and look forward to applying these new ideas to the work we've started, as well as hearing any ideas you might have to help us improve the work we've started. So yes, my name is Jennifer Jacoby, and I'm joined by my colleague Joe Lucas. We are with the Office of Energy Efficiency and Renewable Energy, or EERE, with the Project Management Coordination Office. This presentation is the result of methods and analyses performed with our former colleague Joyce Yang. Before I begin, I'd like to share a little bit about EERE. We are an applied research and development office within the Department of Energy, consisting of 11 technology and program offices. Our analysis today will focus on our 9 R&D tech offices. EERE invests in early-stage R&D of energy efficiency, renewable power, and sustainable transportation technologies. We do this through competitively awarded financial assistance projects with the private sector and direct funded projects with the national labs. EERE has an annual budget of approximately $2.3 billion. We manage about 900 active projects per year, and the average length of our projects is 3 to 5 years. The average dollar per project varies by tech office. We fund anything from small, limited duration R&D to large-scale biorefinery pilot projects. Within our R&D tech offices, the funding is split with about 60% going to labs and 40% to financial assistance. Now, on to the topic at hand. Bibliometrics is a relatively new area of analysis for EERE and is intended to supplement EERE's current impact evaluation template. We're interested in bibliometrics because as an R&D funding agency, we are accountable for the overall science and technology impact that results from our stewardship. One way of measuring this impact is the knowledge products produced during the course of R&D. In addition to measuring those knowledge products, we are particularly interested in using bibliometrics to track the knowledge transfer of publications resulting from early-stage EERE-funded research to later-stage research and commercialization funded by the private sector. EERE aims to fund the gap between basic science and commercialization. So when EERE is assessing our impact, we need to measure not just knowledge products, but knowledge flows. A second reason why EERE took on the topic of bibliometrics was the formalization of public access at EERE in 2015. In order to make our research more readily accessible to the public, to increase innovation, commercial opportunities, and accelerate scientific breakthroughs. As such, researchers are required to make an accepted manuscript of publications resulting from EERE-funded research available to the public free of charge on OSCE.gov. However, in order to assess EERE's compliance with public access, we needed to have an inventory of publications. So those are the two big reasons EERE was interested in bibliometrics. Now let's take a look at how we did it. EERE's biggest challenge in taking on a bibliometric analysis is that we do not have a publication data set at an organizational level. The big problem with our internal reporting is that we do not have a portfolio standard. Thus, it is difficult to quickly extract and roll up publications at a portfolio level. A second option for us is OSCE.gov, the public-facing site of all scientific and technical information created by EERE-funded research. However, in order for the information to get to OSCE.gov, our lab and financial assistant recipients need to submit the knowledge product, and our recipients are unfortunately only about 50% compliant. Finally, Web of Science provides excellent coverage of EERE research areas, and we can use keywords from EERE's standard acknowledgement language to identify EERE publications. The problem with Web of Science is, again, we only have about 50% recipient compliance with proper acknowledgement language. So we went with an all-of-the-above option. We combined data mined from OSCE.gov with that of Web of Science and are implementing process improvement efforts within EERE's internal collection templates and recipient compliance with acknowledgement language. At a portfolio level, OSCE.gov is a very simple search. We just need 3 fields: date, resource type, and sponsoring organization. Our Web of Science search also has 3 parts, but as you can see, the search string is much more complex. Because we have a known issue with proper acknowledgement language, we cannot just search for EERE, because some recipients include just Tech Office or just award number or just the initiative within the Tech Office. And then we have to account for several iterations and acronyms. For example, to assess our solar publications, we need to search for Solar Energy Technology Office, then SETO, the acronym for solar, then SETP, the acronym for solar's old name, then Sunshot, a highly prolific initiative within the solar program. In addition to the funding agency, we also have a wildcard search for EERE's 3 grant numbers, EE, FC, and FG. In merging the data from OSCE.gov and Web of Science, we identify an additional 300 publications each year. I created a little process map for you to help illustrate the steps we take in order to develop the data set we use to conduct our analysis. First, we search in OSCE.gov to identify any publications submitted to OSCE.gov that don't have proper acknowledgement language. Next, we search in Web of Science to capture all publications within EERE identifier in the acknowledgement language. Then we send the data set to the analysts at OSCE who identify any accepted manuscripts submitted for that publication. This helps us verify EERE attribution and also helps us assess our compliance with public access. Next, EERE data analysts pull in award information from EERE's iPortal system. Then comes data cleansing. For any publication not associated with an award number or technology office, I read the acknowledgement language to eliminate false positives. With 5 years of building this data set under our belt, we are at a point where we are starting to use Python to automate steps 1 through 4 and much of the data cleansing in step 5. So that is our method. Due to 2 significant issues with compliance, our data set is an underestimate of EERE's actual contributions. We did learn a lot from this incomplete data set and hope to learn even more when we improve compliance issues. Let's begin by looking at our total number of publications. The bar graph on the left shows you that EERE-funded publications are steadily increasing over time. Note that there is about a 2-year lag in identifying publications at closeout. so we expect to tick up in the 2019 publications. The pie chart on the right shows you the average of publications by funding type. You can see that 54% of EERE publications are attributable to labs, 37% to financial assistance, and 9% are attributable to EERE but cannot be further identified as lab or financial assistance. This corresponds to our funding model. Another metric we wanted to look at is what research areas EERE publications are influencing. You can see here that EERE has 3 dominant research areas: material science, engineering, and chemistry. And there is little change over time for EERE as a whole. Our analysis becomes much more interesting when you look at trends based on publications by tech office. It is very important to note here that the range in number of publications per tech office is not necessarily tied to funding, management oversight, or the value of the project. EERE does not expect the entirety of our research to result in publications. Instead, the value of pursuing a peer-reviewed publication as a research output varies greatly among the different technologies. Thus, a low count of publications from one EERE tech office compared to another may simply be an expected variance due to the different technologies that EERE office supports. Where this information is valuable is in allowing the tech offices to observe trends within their own data set. Look at the steady decline in solar publications, the sharp increase with vehicles and advanced manufacturing. Could the decrease be a sign of the maturity of the technology? Could the increase reflect the research community's interest in a new technology? Or perhaps the change could be an intentional result stemming from a programmatic decision. For EERE, the value in this data is not in drawing conclusions, but in generating questions. Publication analysis is one data point tech offices can use to assess the impact of their research in a 2 to 3 year time frame. As an example, let's take a closer look at solar. From 2015 to 2019, total annual publications decreased by about 100, while funding remained mostly constant. Now, if we take a look at the research areas of solar's publications during the same time period, we see a dramatic increase in engineering from 2% in 2015 to 46% in 2019. Compare the small sliver of blue on the left to the supersized slice on the right. These data points can be used by the tech offices to determine if these results align with their programmatic goals. In addition to the quantitative analysis of our publications, we also wanted to assess quality. We looked at citation rates in 2016 and 2019 for EERE's top 3 research areas. From left to right, material science, chemistry, and engineering. We found that EERE-funded publications earn substantially higher citation impacts than a normal citation frequency distribution. At least 28% of papers published in 2016 and 2019 rank in the top 10 percentile. This is nearly 3 times what we would expect. Even more impressive is the 2016 material science had 37% of publications in the top 10%, and 2016 engineering had 41% of publications, nearly 4 times what we would expect. In order to make this information meaningful for the tech offices, we took a look at when EERE-funded research was most impactful. What you see here compares the age of the grant to the number of citations and shows that for EERE, the sweet spot for impactful publication is right around the 2 to 3 year mark. Identifying highly cited publications in and of itself may not be an end goal for tech offices. However, one way knowledge products are transformed into a clean energy innovation is when a publication is referenced by a patent. The visualization here is based on the research of David Popp and illustrates the timeline of when we would expect a highly cited publication to be referenced in a patent. Popp found that, like EERE, most government-funded energy research produces papers 2 to 3 years from the funding date. He also identified a correlation between highly cited papers being referenced by patents, typically 7 to 10 years from publication date. With our data set, we're currently at the red "You Are Here" marker. So our data set is a little early, and we should be able to observe more in the next 2 to 5 years. Even though it's early, we went ahead and searched USPTO for patents using the titles of the top 10 cited publications in 2015 to 2017. I chose one highly cited article with associated patents to illustrate how our tech offices can begin to use this information. The award we are looking at today is a Solar Award, EE0004946, made in 2011 to Stanford. Searching by award number in the patent databases of USPTO and iEdison, we find 7 patents, 15 patent applications, and 4 inventions. Already, the intellectual property generated by this award is impressive. A less direct path to track intellectual property is to identify EERE-funded publications referenced by a patent. The article we are looking at today is a highly cited Nature publication from 2016. From the acknowledgement language, we know that research from 4946 contributed to this paper. Searching in USPTO, we find 11 patents and 3 patent applications citing the article. These patents do not overlap with the patents we attributed to 4946 through iEdison or USPTO. This is a whole new set of patents that we would only be able to attribute to EERE through the Nature publication. This demonstrates knowledge transfer and indicates that the private sector has used EERE-funded research to further advance the technology. So, since Joe and I both work a lot on process improvement strategies, we wanted to see how we can use this data to collect lessons learned and document processes to duplicate positive results. What you see here are the top 15 highly cited publications. The green represents publications that acknowledge 4 projects, all stemming from the same funding opportunity announcement, or FOA. In this case, FOA 0990. This FOA produced 60% of the top 15 cited publications in 2015 and 73% in 2016. These awards were all made in September of 2014, and their big citation rates are within that 2 to 3 year window. The opportunity here is for our tech offices to take a look at this data and identify trends. They can use this information to initiate a 2 to 3 year retrospective analysis of best practices and areas of improvement in the FOA. And they can identify what publications to watch for potential inventions and technology commercialization. This publication trend led us to identify a possible best practice. For this FOA, submitting publications was a requirement included in the Statement of Project Objectives to encourage research dissemination. With further analysis, EERE can assess if this is a best practice that we should encourage all tech offices to adopt. Another process we can analyze using the publication data set is EERE's compliance with public access. The image you see here shows the total number of EERE publications over the 5 years the public access plan has been in effect. We can now document that EERE-funded publications are increasing, and compliance with submitting accepted manuscripts is also increasing. Moving forward, we plan to continue our annual publication analysis, use this data to identify process improvements and best practices, improve recipient compliance with accepted manuscript submission and acknowledgement language, and standardize our reporting, while also implementing post-project reporting compliance. Okay, that's all I have for today. Thank you so much for your time.
Thank you, Jennifer. We do have one question coming in. So are you aware of any EERE-funded publications that are not indexed by Web of Science? And if so, what are some of the journal's characteristics?
No, we are not. I'm not aware of that.
Great. Thank you. One more question. It seems that authors are not always including appropriate funding acknowledgements in articles and patents and not always complying with the public access policy. Have you investigated why not?
I believe our recipients are much more compliant with patents, and that is partly due to EERE's efforts in that area. So I apologize if I confused anyone by that statement. With acknowledgement language, as well as submission of accepted manuscripts, I think it's twofold. It's partly EERE. We need to do a better job communicating that requirement to our recipients and helping them with, these four. We always want to hear EERE, the tech office, the initiative name, and the award number, and that allows us to better track our impacts. So we've created a lot of resources for recipients as well as EERE staff, so trainings, tip sheets, reminders. But I think it's just due to education and outreach efforts.
Thank you, Jennifer. We still have a few questions in the chat, but I think we have to move on. So please go to the chat and look at the questions and see if you can communicate with the audience. Thank you.
Great. Thank you.
Yes, and thank you again, Jennifer, for a great presentation. So up next, we are going to move to Chris Wolcott from Digital Science to talk about a data science method for identifying data science projects. So Chris, are you there?
Yes, I'm here.
Great.
All right, great. Thanks, Chris. Thanks, Chris, for the introduction. As he said, my name is Chris Wolcott. I am an analyst at Digital Science. Today, I'm going to present some work we did in collaboration with the National Institute of Allergy and Infectious Diseases, where we're looking at data science methods to identify data science projects at NIAID. So to start, I'm going to talk a little about what is data science and some of the challenges we ran into. We're considering what a data science portfolio at NIAID would consist of. From there, I'm going to talk about the approach we took to categorization, how we developed that, and how we decided to scale that. And at the very end, I'm going to present some very preliminary data science portfolio views we can come up using this new method. So data science as a topic, everybody knows, is a very rapidly growing and evolving concept. It's recently become an explicit focus at NIH starting around 2018. However, data science is not actually new. It actually encompasses a lot of techniques and tools that have been used for decades. And so when we ask the question, what is data science, it's actually very difficult to answer because we have something that's both old and currently growing and evolving very rapidly. And so when we ask that question, the answer really depends who's asking. For this project, we're working with NIAID, and so we want to say, what does data science mean at NIAID? On this slide, I have a summary of a much larger definition. But really, I want to hit the key points of that. These are things that are primarily computational and one or more of these subcategories. I'm not going to spend a lot of time diving into what these subcategories are, but I do want to talk about how we came up with this definition because it in itself is one of the big research outputs for this project. So typically, when we're trying to identify a topic and a portfolio for that topic, we go with the coding process, something like laid out in this cartoon in the center. We start with a concept definition, and then we have subject matter experts who look at that definition, look at a set of documents, and then apply coding based on the definition. While they're doing that, the subject matter experts might realize the definition needs to be revised. Things need to be added, things need to be removed. And over the course of many years and a lot of coding, you end up with a very nice, robust definition, as well as a very nice set of documents that really represent what that definition means. And so we're working on this challenge with NIAID. The question we're asking is, how can we try to understand NIAID's data science portfolio today without waiting for years of manual coding by subject matter experts? The approach we took was to say, let's try to develop a machine-assisted method to help speed this along. The figure on this slide is very similar to the one on the previous slide, but with a little more detail and a couple extra steps. It's very similar overall. We start with the definition. We then try to identify some documents that are extremely strong examples of that definition. We then try to develop some method or model to identify those documents and other documents like them. And then we expose these results to subject matter experts and try to get some feedback. In this whole process, we're iterating on this a lot. We keep going back and we update our definition, we'll update our example documents, we'll update our methods. And hopefully at the very end, we have this very nice machine-assisted definition as well as a coded data set which we can conduct analyses on. Now for this project with NIAID, we're actually currently on this fourth step. We're waiting for validation. And so Later on, when I do show you some preliminary results, please keep in mind that final validation of this method is still forthcoming. For most of this talk, I'm going to be talking about this third point, how we construct these models and methods. So what we're doing here is we're really trying to say, let's have a computational approach where we can score applications based on this definition of data science that we've come up with. We evaluated a lot of different tools to try to do this, and we ended up settling on the three I've highlighted here. Very quickly, the NIH RCDC tool is a tool which allows us to apply RCDC fingerprints to NIH applications. We identified 3 RCDC categories that overlap well with our definition, and so we used the scores from those 3 RCDC categories as our weight for that one. Dimensions keyword query. For those who don't know, Dimensions is a part of digital science, and I'll talk more about it in a few slides. But one of the many things Dimensions includes is a large body of grants and NIH applications which we can search with a keyword query. So we develop a keyword query based on our data science definition, and we get back a set of documents along with relevancy scores. We use that as our weight for that method. The last one of these is the LDA topic model. I'm going to go through this one very quickly, but it's quite sophisticated. LDA topic model is an unsupervised machine learning approach. You feed in a very large corpus of documents, and then the machine tries to identify topics in those documents based on things like term co-occurrence. Once it's identified all the topics, it then goes to each document and assigns a weight in each topic. By looking through the topics we found when we did this, we identified a number of topics which are relevant to our definition, and we used the weights in those topics as a score for this method. Looking at all these 3 methods together, we saw there was a lot of overlap between them, but also each of them was picking out things on their own. And since we really wanted to get as complete a view as we could, we had to use all of them together. We couldn't just pick one. Simultaneously, when we were developing all this, we had a number of manual coding exercises going on, and we were able to see that there was a correlation between the scores we got for these methods and what subject matter experts coded documents. And so basically we could say if the score is sufficiently high, it's data science. If the score is sufficiently low, it's not data science. And we also identified a third region in between where we actually had a lot of cases where subject matter experts disagreed, and we labeled these as indeterminate. These are cases where we think if human beings can't agree if they fit the definition, the machine is unlikely to do better. So for this project, where we are right now is we're still waiting on the final validation of this approach right here. We have gone through several iterations. All the results are very promising, but again, that final validation is still forthcoming. While we're waiting on that, though, we were looking at this method and said, what are the challenges of this method? And what makes this method difficult to use? And really, the challenge is that it's cumbersome. We have these 3 separate approaches. They rely on proprietary tools that are only applicable to specific data sets. And each of those tools actually has an underlying infrastructure which can change over time. And so it's very difficult to reproduce our results. Knowing that, we said, let's try to use a simpler approach. Let's try to use a simpler machine learning model to replicate this process. And so what we're going to use is we're going to build a very large set, which we machine code with this current method we have, and then we just use those codings and the document text as input to a machine learning model, and we try to approximate this more complicated method. The set we ended up building is based on 5 years of NIH projects data with activity codes related to either training or research project grants, and the final coding breakdown is shown in the bottom in the center. Once again, I want to call it these indeterminate projects. These are the projects where even subject matter experts who look at these can't agree if these fall into the definition or not. When we're introducing this to our machine learning model, we have to give these special handling because if we code them one way or the other, it's likely to confuse the model and make the model perform much worse. And so for the sake of training the model, we've excluded these. So we have a cleaner break between things that are data science and things that are not data science. This slide has a lot of details about the machine learning model. I'm not going to go through all of those right now. I just want to highlight the performance shown on the bottom. Particularly, I want to show in the bottom left, these are performance metrics for how the machine learning model is doing. Overall, this precision recall F1 score all say this model is actually doing very well. So the machine learning method replicates that more cumbersome approach very well. We have a higher precision than recall, which is very much what we expect and what we really want. Precision tells us that if we make a prediction that something is data science, it actually is data science. The recall is a little lower, but it's still quite high. But this means that there's going to be some data science projects which we're missing, but that's okay because we really would rather be correct than complete. So we have this method now. What can we do with this much more scalable method in the machine learning model? What we're going to do is we're going to apply it to a much larger data set and try to get some global and historical perspective about what's happening in this topic. To do that, we're going to use dimensions data. Dimensions is a part of digital science. Dimensions is a database that includes a large variety of different research inputs and outputs, some of which are laid out here. In addition to collecting all of these things in one place, Dimensions provides a lot of enrichment to the data, including, most importantly, linkages between them. That we can say things like grant A funds publication B, which is cited in clinical trial C. By having all these interlinkages, we can do a lot of very interesting analyses very quickly. A little bit more about Dimensions. There's a lot of different data in Dimensions. We're going to be focusing on Dimensions grant data. We're also going to be leveraging some of this other enrichment in Dimensions, particularly when you use these research categories, where all documents in Dimensions are automatically assigned to research categories in a variety of categorization schemes. The reason we're going to leverage these is because when we started, our model trained only on NIH projects data, which are all biomedically focused. We're going to use these categories, so we're only searching Dimensions grants that also have a similar biomedical focus. We really don't want our machine learning model to try to predict whether an astronomy paper is data science or not, because it hasn't seen any astronomy papers before. So if we use that, we narrow Dimensions down to biomedical grants, and then we apply our model to find out whether those are data science or not, and then we look across time and see what's happening in this space. And here we have the fraction of biomedical grants that are data science over time for the past 10 years. This figure isn't terribly exciting, but it is actually very comforting to us. We know that data science has been around for a while, and we see that it does exist going back. But we also know data science has recently become an area of special focus in a large number of different areas, and so we should expect to see a rise in recent years. And that's exactly what we see, where it goes from a little over 4% to about 7% today. So from here, we try to zoom in a little bit more and say, what do these grants that are active in 2020 actually look like? And so here's by that data broken down by who's funding this research. Left-hand side is all biomedical grants in Dimensions active in 2020 by funder. Right-hand side is that same data, but now subsetted to those which our new method has tagged as data science. Again, some comforting things here. We see things we expect. We know NIH is a dominant player in this space, and that's exactly what we see. We also see some other interesting things like some of these other funders, NSF or UKRI, seem to have a much smaller presence in the biomedical space, but when we go to this biomedical data science space, they actually become much more significant. Now, this is still preliminary results. We would need to go and validate all of that if we really wanted to say something concrete, but as a preliminary result, it's very interesting. So now let's zoom in a little further. Let's look at NIH, and let's particularly look at NIAID, since they're the ones who are working with this project. When we look at the NIAID portfolio in 2020, we see that it's a little bit above 2% of NIAID's projects are data science. Now, what does that really mean? It's actually hard to say without any context. And so to get some context, we're going to apply the same method across all NIH ICs. Here we're looking at data science focus, which we've calculated as the fraction of data science projects at NIC compared to the fraction of data science projects at NIH overall. Again, as a quick gut check, we look at this and say, the ICs, which are very data science focused, are actually those we expect based on just conceptual understanding of what they are. So National Library of Medicine, Human Genome Research, Bioimaging, these are places where we would expect conceptually to have lots of data science projects. Now we can look at this and see NIAID's number is actually very low. And so that's definitely a very interesting takeaway. I do want to caveat this again that these are preliminary results. Final validations is still forthcoming, but as a preliminary result for us, this is very interesting. All right, and so with that, I'm going to jump to conclusions. We've shown that we have this machine learning model that provides an excellent approximation of this much more complex method and does that without relying on any proprietary tools. It's easily scalable to very large sets of documents where all we need is title and abstract text. I want to remind everybody that model validation is still ongoing, but preliminary results are very promising. Using this model, we'll be able to see some things which give us some comfort and also are sort of interesting on their own. So we've seen that data science and biomedical research is rising in recent years. We see that NIH dominates in the global biomedical grants data that was up in, as well as in the biomedical data science grants, but a couple other funders emerge as significant players. And lastly, we've seen that based on these preliminary results at least, NIAID's data science portfolio is pretty small. So with that, I want to thank everybody on the project team. For the sake of time, I'm not going to call out everybody's name, but thank you, thank you, thank you. I want to give a quick plug. There is a Dimensions training session later today, and with that, I will open the floor to questions. Thank you.
Thank you, Chris. We have two questions, and they're related. So the first one is that, is there any documentation that is available that further describes your model? And the second one is that, are you aware of any model that is similar to yours that have effectively classified subject areas in research paper?
So while we're working on this, there was a paper which came out by some people, I believe they were at OPA and working on an NHLBI data science project, where they had a similar sort of approach using some different tools where they were trying to capture a data science portfolio. I think our definition and their definition aren't quite the same, which is really the big important sort of takeaway for why we don't get the same results. As for documentation, I would say if you have questions, ask, send an email to the address on this page, and we can get you some more information. That's all I'll say for now.
Okay, and another follow-up question is that, have you validated your model? How did you do that? And in your training set, how do you decide what data is ambiguous and should be removed from the training data?
So we used a variety of coding exercises where we had subject matter experts code sets of documents, often multiple subject matter experts coding the same documents, so we could try to get a consensus. From there, we sort of looked at just a correlation between how did our scores, what did they code as data science align with our scores, what did they code as not data science, where did that align with their scores, and then just as importantly, where the subject matter experts disagreed, how did those ones where they disagreed align with our scores? So that's where we came up with all of those thresholds to come up with those codings. As for validation, it's the same process. We are still going through and having subject matter experts actually go back and look at these results. It's a slow process, which is why we don't have final results quite yet, but it's forthcoming. So,
thank you. One last question is about slides sharing. People are wondering if you're going to share with them and where.
So we don't want to make these slides publicly available because we haven't, because they contain so many preliminary results, but if someone would like a copy of the slides, we are open to sharing them. Please just send an email to dimensions@nih.gov asking, and we'll get back to you.
Thank you, Chris.
All right, thank you.
Yes, thanks again, Chris. That was a great presentation. So our final presentation in this particular set of presentations is from Holly Falk-Krzesinski from Elsevier and the International Center for the Study of Research to talk about approaches for studying gender in research. So Holly, are you there?
Yes, I am. And are you able to see my slides?
I can hear you, but I don't think you're sharing your slides quite yet. I made you the presenter, but you're not sharing yet.
Okay, hang on. We want to share.
There you go.
All right, now we're good.
Yep.
Okay, now you guys should be able to see.
Yep, take it away.
All right, thank you so much. I really appreciate the opportunity to be here and to talk with all of you. Today, it's my pleasure following up on Cassidy's great keynote from earlier today, methodological approaches to studying gender in research, and I'll be covering an overview of 3 different studies. The first study is the Researcher Journey Through a Gender Lens, which you can find available at this URL. It's a culmination of analyses examining gender in the research participation, career progression, and networks across the European Union and 15 countries globally in 26 different subject areas across all disciplines in the social sciences, the life sciences, the medical sciences, and the physical sciences and engineering. This report offers powerful insights about the role that gender plays in the global research enterprise and is intended to inspire evidence-based policy and interventions and inform further data-driven studies. We use the Scopus database for the majority of the analyses within the report. Each author in Scopus has a unique author identifier or author ID through which we can identify all the name variations, publications, affiliations, and citations of an author to form a disambiguated profile for each. This allows us to compile for authors a full name and the first country in which that author is published. For more details about Scopus, please refer to this 2020 QSS article that I'm showing here online, or tomorrow at 3:45 Eastern Time, please join the session in which I will share much more detail about Scopus. Throughout the report, we employed an inferred binary gender designation approach that combines the Scopus database and an API-based gender disambiguation tool, NameSOR. We conducted gender analysis at the individual level and report our findings at an aggregate level throughout the report. NameSOR in particular, and the reason we used it, is that it looks at given names, surnames, and if available, country of origin, which we use the country of first publication as a proxy of a person, and returns a score that classifies the name either as man or woman, providing the probability that each name is masculine or feminine. All Scopus author profiles for which a full name is available were run through the NameSOR API. If the first name is associated with the gender, then more than 85% probability, that author was assigned a predicted gender. Otherwise, the gender of the researcher is not identified and those authors are not included for further analysis. This methodological approach allowed us to investigate the participation of women and men across countries and regions around the world, where we saw that women's participation is increasing around the world, but at different pace in different geographies. So here on this screen, you can see the orange and the bright red lines, Argentina and Portugal, are in the lead compared to the light pink all the way on the right-hand side, which is Japan, which is far behind. The squares representing an earlier time period and the circles representing the later time period. So there's definitely some good news that the representation of women is increasing over time. However, we also observe differences in women's representation in research fields, across research fields. Here you can see the median ratio of women to men in each country in 4 different representative subject areas. These data show that women are least represented in the physical sciences and engineering, where we saw in another set of analyses that aren't shown here, the rate of participation growth is also the slowest in engineering. This is in contrast with what we saw for medicine, biochemistry, and social sciences, fields in which the gender ratios are closer to parity. This data tells us that we cannot think about all fields in the same way in which we consider interventions and policies to address the underrepresentation of women in research. And even more noticeably, here I'm just showing is that we investigated those fields that are related to data science and AI, notably computer science, mathematics, and engineering. And we found that not only are women the least represented in all of these fields, but gains for women in terms of the growth of representation is the smallest across all 26 fields. We were also able to examine cohorts of researchers by career age, in which we use year of first publication as a proxy for age. We saw that women are most well represented in early career cohorts, that is the lightest purple circle. And in an accompanying analysis that I'm not showing on this slide, we found that women leave research at a higher rate than do men over time. This approach affords us the ability to conduct longitudinal analyses to investigate trends and changes over time, and doing that for different cohorts over time. The Scopus database also allowed us to examine representation by authorship position. We found that women are least represented as last authors, corresponding to women's lowest representation in senior cohorts. And we were able to do even more sophisticated network analyses in which we found that men have more direct collaborators than women, not something I'm showing on this slide, and that homophily, or the birds of a feather phenomenon, is in play when it comes to collaboration, in that men tend to collaborate with men more and women tend to collaborate more with women. This data offers evidence-based and actionable insight that can be used, for example, to develop institutional level interventions related to faculty members and their professional network development. It also tells us that while there is an increased participation of women in science, women's inclusion in science is not on par with men. Switching gears, we conducted another study to understand, considering both sex and gender, the populations and models focused on in Alzheimer's disease research. We were inspired to do this because the literature reports that Alzheimer's disease is a much larger burden for women. In this study, we analyzed full-text journal articles from the Science Direct platform, which contains over 7,600 articles about Alzheimer's disease research in just the 2014 to 2018 period. We mined articles' methods sections to identify and categorize studies as research focused on women or females, research focused on men or male subjects, or both, a corpus of about 2,500 different articles. And you can find that full report at the URL that I show on the screen. Terms related to sex or gender in the article method sections is indicative of the use of human and or animal systems. Among the publications that mention sex or gender terms, the majority of research focuses on men or male subjects, 80% of the studies, in fact, and exclusively in almost half of them. Comparatively, women or female subjects were included in only 51% of studies and exclusively in only 20%. And only 31% of the studies used both male men and female women subjects. We further analyzed those articles and categorized them as studying human subjects or animal models and found that the difference that we saw on the last slide is most prominent in animal studies. 62% of research using animal models mentions males only, while 14% of research mentions females only. This is a finding with really great significance and concern, given that animal models facilitate the discovery of new drug targets and sex-related factors can influence drug-related responses. Also, because sex and gender analysis and research is so important, we've recently launched a public Mendeley library focused on COVID-19 studies. And you can access that public library at the URL here, and I'm showing on the right-hand side just some of the folders that are in that library now. And finally, our most recent study, it's an examination of the extent to which research across the UN Sustainable Development Goals includes consideration of sex and gender. This study was done using the Scopus database and had 3 steps. We identified research related to each of the 16 SDGs using existing Scopus SDG queries, which are all publicly available. We then built a new sex and gender keyword search or query, and that can be applied to Scopus as well. And this is work that actually builds on findings from our 2017 Global Gender Report. And then we overlaid the 2 resulting data sets using a VOS viewer tool to visualize sex and gender overlay maps for each of the 16 SDGs. The 16 SDG queries for Scopus already exist and are open and free to download, as I've already noted. We invite you to engage with us, in fact, to contribute to the public data sets of research that supports the UN SDGs, and more details are at this QR code and the link that's on your screen. To build the new sex and gender query, we drew keywords from publications within the Gender in the Global Research Landscape public Mendeley library and combined that with expert input from Dr. Elizabeth Politzer of the Portia Limited and the International Gender Summits. The results in query is shown here, and we'll be uploading that to Mendeley data shortly. But in the meantime, of course, we'll be happy to share my slides and the query with anybody. In the table here, the 16 SDGs are listed along with the count of publications identified by each SDG query in Scopus, and the count of SDG corpus of publications that also include those publications identified by the sex and gender query, and then the overlap proportion, the share of SDG research that also covers sex and or gender topics. The figure on the right graphically presents the data from the greatest proportion of sex and gender research for SDG, which is SDG 5 or gender equality, to the least. And that is, unfortunately, affordable and clean energy. What we saw is that only SDG 5 and SDG 3, good health and well-being, are the only SDGs with more than 60% of the publications factoring in sex and or gender research. Using the SDG queries for Scopus article titles and abstracts, we identified the publications that comprise the SDG targets and indicators. That is the research corpus for each SDG, and that's what you're seeing on the left, the SDG 5. Terms from the SDG corpora were mapped, resulting in figures like the one on the left, and the colors indicate topical or thematic clusters, or nodes, different areas of research within each of the SDG's research corpus. On the right is the sex and gender overlay map, the proportion of publications within that SDG research corpus that were also identified by sex and gender query. The color scale refers to the share of sex and or gender research overlay score. Most of this SDG overlay map is yellow. This is illustrative of a high degree of overlap between the SDG publication sets and those publications within the corpus tagged as also being identified by the sex and gender keyword search. And since this is on SDG 5, which is gender equality, this wasn't a particularly surprising finding. We, though, went ahead and examined all 16 SDGs employing this exact Scopus-based query and overlay mapping methodological approach and saw a considerable variation. Even for SDG 3, good health and well-being, research has an uneven inclusion of sex and or gender consideration. The terms in SDG 3 that do not include sex and or gender, the green and blue nodes that you see at the bottom of the map, those are clusters that relate to fundamental and basic biology, as well as public and environmental health. This is consistent with what we saw in the Alzheimer's disease study, and unfortunately, despite calls for sex and gender-based analysis and research across the spectrum of life and biomedical sciences and human health research by major biomedical funders across the globe, such as the NIH. This study overall provides a benchmark for the development of inclusion of sex and gender considerations as a critical dimension of sustainability research, and the methodology can be employed to measure and compare ongoing progress of sex and gender-based analysis within and across all 16 SDGs to ensure rigorous results and inclusive, impactful policy. Now, importantly, I want to make sure that if you are interested in conducting sophisticated non-commercial research analyses like those I've shared with you from any of the 3 studies on your own, you can actually submit an application for no-cost access to the ICSR lab at the International Center for the Study of Research. And the URL for access is up there at the upper right-hand corner. And importantly, the gender field that has been assigned to Scopus author IDs is an available metadata field within the ICSR lab. Moreover, here are the links to the reports, studies, libraries, and lab that I've shared with you today, and some additional gender and research resources. I've already mentioned the Gender and COVID Mendeley group. There's also within Elsevier our gender working group, which I'm very proud to be co-chair of, in which we really work and focus on the activities of gender inclusiveness and diversity and equity across all of our publishing activities. And coming soon in that realm and following up on some of the work that Cassidy and her colleagues have done, we've done a COVID-19 impact on article submission across Elsevier's full journal portfolio, all areas and disciplines, and have already identified differential effects, negative, for women. And we've now submitted that research article, and we are hoping that it will be published soon. With that, I want to say thank you, and I want to point out to my significant collaborators who did lots of the work that I had the pleasure of being able to share with you today, notably Dr. Bamini Jayabalasingham here at Elsevier, our full gender report team, and then my colleagues at the International Center for the Study of Research, Rachel Herbert and Andrew Plume. And with that, I'm happy to answer any questions that we have in the few remaining minutes that we have left.
Thank you, Holly. There are 2 questions, but they're basically addressing the same thing. So since that there is a drive to recognize non-binary genders, so how is that going to affect this type of studies?
Yeah, so it will make this kind of studies even more robust. Look, there are some limitations in how we can conduct bibliometric assessment when we are using inferred information. We are separately looking to do in a number of our systems, though, work out ways in which we can capture information directly from individuals with regards to gender identity. And we hope that into the future to be able to combine those 2 data sets. So while we recognize that it's definitely a limitation and not perfect, we don't want to let perfection get in the way of doing very important work at looking at the bias and discrimination and unequal representation between genders across research disciplines. And importantly, data like that within our global research report, the researcher journey through a gender lens, that there are differential differences. That is, we can no longer really, and in good conscience, make sweeping conclusions and claims like women are just underrepresented in STEM and we have to do something about it. What we know, in fact, is that there are some fields in which women are more well represented and other fields where they're really significantly underrepresented. And we need to think about our differential approach to addressing that problem. And I don't think that we're limited in being able to think towards those goals, even with only a binary gender model that I've applied here in all of these studies.
Thank you, Holly. One last question is about sharing your slides and materials. Would you be willing to share?
Yes, I will happily do that. So give me just a moment, and I will, I'm not a big Slack user. I'm going to do my very best in a moment to share the slides as PDF on the Slack channel. If that doesn't work very well, then I'll put my email address and people can ping me directly. But of course, we're very happy to share all of those. And I invite you to send me any additional questions that you have about any of the 3 studies, the data sets, or a methodological approach to any of them.
Thank you very much, Holly.
Thank you.
Actually, Holly, it looks like we've got one more question, and I think we've got some time for it. So NameSOR gives a predictive country. So have you compared the NameSOR predictive country in the first country of publication?
Yeah, so what we did is override that, is that what we used is the first country of or the country for the first publication is what we used as the country of origin in our global gender research report. And so that was the approach that we took, rather than the system trying to predict what the country of origin might be. We used a different proxy indicator in that case.
Great, thank you very much. So that concludes our panel session for this particular time slot. So thank you all again for all of the participants, and thank you very much to all of our presenters for presenting today. So we'll again take another 15-minute break, and we'll reconvene at 45 minutes past the hour for our next training session on from digital science on the Dimensions database and platform. Thanks.